Question 7, more nuclear stuff. This time it's radioactive decay. So we've got tritium nucleus decaying by beta. Complete the decay equation. So first things first, this is turning into helium, we're told that. And helium must have two protons, otherwise it just isn't helium. This is beta decay, and beta is the kind of 0 - 1 setup. So, you know, top line just balances. So it is that isotope of helium that we're looking at. And to completely balance this, we need the antineutrino as well. And that's that. The molecules of a gas consist of two of these atoms. Yeah, tritium too. The gas has a volume of yada yada and a pressure, so that the number of nuclei is approximately that. So here we've got PV equals nRT, making an unexpected appearance. Therefore, N is PV over RT. So we'll put in our pressure, 227 times 10 to the 3. Our volume, 17.2 times 10 to the -3. We'll divide by RT. I suppose I could have used NKT, actually, couldn't I? Should I use NKT? Since we're after, I'm going to use NKT, sorry. I mean, it doesn't really matter. I can just, no, I've started, I'll finish. So I'll convert using Avogadro's number. 831 times temperature. But you could have obviously saved yourself a step and used NKT. So that's going to give me the number of moles, and then I'm going to multiply it by Avogadro's number. 1.60 moles. 1.60 times 6.02 times 10 to the 23, Avogadro's number, is equal to 9.65 times 10 to the 23. Oh. Interesting. Ah, right. So that is how many molecules. Okay, that's the number of molecules, sorry. So there are twice that many. Double that as our number of actual nuclei. Okay. I thought for a second I'd gone horribly wrong. Good thing that's a show that. Otherwise, I think I'd have just left it and went, yeah, it's that. Right. What is it? The tritium nucleus has got this half-life. Calculate the initial activity. So be a little bit careful. We want activity in becquerels, so we want it in per second. And here we're given half-life in years. Does the formula sheet give you a seconds to years conversion? It doesn't, does it? Don't think. It doesn't give you anything like that, I don't believe. It'd be handy, wouldn't it? It would be pretty handy. But no, doesn't. I'm sure I've seen that though. Maybe some questions give you that. Maybe there's questions that tell you how many seconds are in a year. Anyway, not a problem. Calculate the initial activity. So we have got a number of nuclei. Activity is equal to lambda n. Lambda is equal to natural log 2 divided by the half-life. which equals log 2 over 12.32 years times 365 days times 24 hours in a day times 3,600 seconds in an hour. Therefore, A is equal to, and let's put it in the calculator at this point. No, not that calculator, not that at all. I don't know what I'm doing. I've got very poor calculator skills, I'll be honest. Where am I? 1, 2, 12.32 times 365. Sometimes students ask me if you need to do 365.25 or not. And generally I say it doesn't make any difference because it's not going, your answer is going to be to 3 significant figures. And it's not going to make a difference in those 3 significant figures. So that comes out at 3.44 times 10 to the 15. And our units here are becquerels, although I suspect you'd get away with seconds minus 1 if you can't remember becquerels. Calculate the time taken for the activity to drop to 10% of its initial activity. So this is the equation we're going to use. A equals A naught e to the minus lambda t. And A over A naught is equal to 10%. So 0.1 equals e to the minus lambda t. Therefore, e to the lambda t is equal to 1 over that, which is 10. And t is therefore equal to natural log of 10 divided by lambda, which is, I've lost lambda, where's lambda? Oh, what's happening here? 3, oh no, I never actually wrote it down. Where's my lambda? It's in my calculator, luckily it's in my calculator. It was 1.78 times 10 to the minus 9. Okay, that is a long time. Of course, it's in seconds. 129. How do I put my calculator in a sensible mode so that it gives me this in standard form? Where are we? Display scientific 3 sig figs, please. Go. 1.29 times 10 to the 9 seconds, and if you want you could turn that into a number of years or whatever, and it is 41 years roughly. Quite a while. Okay. Pions are also unstable. Oh, good Lord, it's a 6-mark QER. I wasn't expecting that. And can decay according to the following equation. So 2 choices here depending on the pion. This one's a pi plus and has got some charge to get rid of. Discuss both these decays in terms of conservation laws and forces. So 6-mark QER like that, discuss both. So what I'm going to do is literally just write as headings pi plus decay. That's my first heading, and then somewhere halfway down the page pi 0 decay. In terms of conservation laws and forces, so yeah, what can we say about this pi plus? It is a meson, so baryon number 0, lepton number 0. has charge +1. To conserve charge and lepton number of 0, this needs to decay into, it's going to decay into particles which are not baryons and which have a total lepton number of 0. With total charge +1, total lepton, 0. This is a weak interaction. They haven't actually told you the full story here. So what would actually happen here is this, I mean, I don't think they want this for this answer, but you know, you guys know that a weak interaction causes a flavor change. So this pi plus, actually I'm going to include that. Composition of a pi plus is up anti-Don. So what actually would happen is this would emit a W plus, which would change the flavor of one of these. So the W plus would, for example, flip this anti-Don to be an anti-up, which would create therefore a pi 0, which would then decay like this. But they've kind of brushed over that. So this decays via weak interaction into E plus VE with charge +1 and 0 respectively. And lepton number -1 and 1, hence conserving baryon, lepton and charge. What else am I going to say? I've mentioned the force, I've mentioned the composition, etc. Pi 0 decay therefore is also a meson. Meson composition, it's either up anti-up or down anti-Don. Can't tell. Up anti-up or down anti-Don. Baryon 0, lepton 0, and charge 0. So with that in mind, it decays as we just have an annihilation here, where you can't, you know, you can't annihilate an up anti-Don. You have to first flavor change one of those. So maybe you flavor change the up into a Don, or you flavor change the anti-Don into an anti-up, and then decays in annihilation, and then they annihilate via the electromagnetic force. With the production, therefore, of 2 photons charge 0, lepton 0, baryon 0. I don't know what else I can really say about that. Not much. Yeah, it's this one I'm finding pretty dubious. You know, and this is kind of the problem with this as a topic at A level. The kind of simplification of some of the processes leads leads to some inconsistencies. You know, if this is a weak decay, where's the flavor change? What happened to the pi plus? It didn't just stop existing. It actually flavor changed into a pi 0, and then that happened. So I don't think it's necessary to say that, but that seems like a pretty straightforward 6 mark QER to me. And that's it.